we'll be able to give Luis all of the time he wants. High-resolution model satellite radar space and time scale cloud organization, the Santa Maria case study. It's from Luis Machado and Chaburó, Jean-Pierre.
So, yeah, we have. So this is it's also a preliminary study, and using also the Santa Maria campaign, and in this effort that was shown by Christoph. So. And you start to study just to compare, and so I gave two titles. That is the effect of turbulence on cloud organization, or also it's to prepare to evaluate the models. So I start. This is a participation with Jean-Pierre Chaburó. It's the work being done in Toulouse. So we have used the Mesenache. It's the scientific magic scale model high resolution from France, developed in Laboratoire d'Aérologie. So it's the magic scale model, this is the reference, it's version 4.9. And so it was running for Santa Maria case in two ways, interact grid, one with 10 kilometers and another one that we have used is 2 kilometers. That was the definition, the same grid of all resolutions models for the simulation shown by Christoph was 2 kilometers with the same grid of 500 by 500 grid points. So 62 levels, the initial boundary conditions were provided by the European Center, and the forecast was done for 12 UTC to 36 hours. So the mods include the turbulence parameterization, add diffusive Kent-Fritz parameterization scheme for subgrid shallow convection, and a mixed phase book microphysical scheme that also provides 6 water species, ice, crystal, snow, grail, and all these guys are from the same lab, so it's easy to contact and discuss this. Utility to make the intercomparison, and the model was run with 1 and 3-dimensional turbulence by Diedorf, using different mixed length inside the cloud, and 1-dimensional turbulence using Bujold and Lacan. So this is the simulations, and here is the we have selected for Santa Maria 6 golden day cases. I will show some results for the 6 cases. And this is just one example for the day 30-35, that is the 28th, it's the 3rd November to 2 December. So this is the image seen by Meteosat second generation. Of course, it's much worse than the model, that was not missing date. And the mesoscale model, the Mesenache output. So it's the same color scale, and you can see that the blue colors are the clouds organization. You can see that model actually was showing the same by Renato, also showed the same case here. So you see that there is some delay, but the representation is pretty well. This is from the radar. This is the same for, this is the Cambuçu radar, 2 kilometers cap, and this is the simulator structure from the meso-scale model. So you can see that also the real data is much more worse than the model. Model is much more well behaved. And, but you can see that some structures are pretty well observed. And I don't know if you can see, but something that appears that you have a lot of small clouds and when the real life is much more organized than the real life. And so this is the histogram from the brightness temperature for the model in blue and the satellite. So what you can see that the satellite, this is for the 6 golden day, the 307 to 345 Julian day. You can see that the model has much more clear sky, that this is a warm temperature. And in this part, the model has the cold temperatures, deep convection near the same. Here is the middle layer of clouds, near the same. In missing parts here of the cold clouds, that you show that it's more the clouds not associated with rainfall. It's more these deep cirrus clouds and stratiform. And here it's the cloud organization structure from the model and from the satellite. So here is the life cycle duration, and here is the size of the rain cells. So what you can see that the satellite, you see this is the distribution, big guys here, and a lot of small guys, but the model does much more small cells than the reality. This is the point that is what model is doing. It's much more small cells, and something need to be turning in the model to fit the same size. At the same time, does not show the big organization with the same size. Here is the life cycle duration. You can see also that the model has much more short life cycle duration than the reality shown by the satellite. So we trying to understand what are the possible reasons that you have large number of small and short life cycle duration of the cells by the model, do not reach the size of big cells as observed by satellite. It's smaller population of cold cloud top that does not show in the model. Small cells simulated by the NOV have very deep cloud top. So this is small guys. There has a lot of small guys, but very high and very deep that was not observed in the reality. So the possible reason we identify is that there is a problem with entrainment. If we increase entrainment, we can decrease this number of small cells and then try to solve the problem. So we start to have some sensitivity studies for 1D turbulence, that was the simulation show, and we move to 3D turbulence. Because here it's a paper that shows what is solved by the model. This is what they call the gray zone, that's this turbulence kinetic energy. And here is the size of the grid. So here you are in 3.2. So our model run with 2. So it's mostly of the turbulence. It's not so explicit. Here is what is so explicit by the models is reach the less simulation size of 100 meters. And here it's mostly of the clouds are not solved the turbulence, so you need parameterization. So what you are going to propose here. And so we run the model. Here is 1D turbulence, here is 3D turbulence. So you can see when you add the 3D turbulence, clouds are more and more organized because you have more turbulence, so you have much more entrainment. It's not a direct adjustment entrainment, but just increasing the turbulence. So the result is clear that clouds more organized in 3D turbulence. And here it's with the radar for 1D and 3D. It is also, you can see that we decrease this large number of small cell, and also you can see that some convection it's produced here instead of 1D was not provided. So we have a different field, and so we start to compare what is the solution with 3D and 1D turbulence. So it's the same as I showed, but including the 3D that now is blue. So the blue was expect to have more clear sky. There is more medium level clouds, but in this part does not change too much, as you see. So you have more clear sky, low level clouds, but near the threshold of 235 Kelvin does not change too much the distribution of the reflective, the brightness temperature. And here is using the radar. So it's this is the histogram for the reflectivity from the radar, and this is the model 1D, the normal simulation. You can see that you have much more reflectivity here, and when you do the 3D, it's approach, but not enough solution to solve the question. However, when you see the distribution of life cycle duration, you can see that the adjustment of 3D just makes nearly the same distribution of life cycle duration of the cells, reducing the life cycle duration of the small cells. And the bigger one, it's hard to see, but it's increased the duration of the big one. You observe in the night 19 hours duration, here is 6 hours, and 1D was 13 hours. So it's increased the life cycle duration for the big one, decreased for the smaller one. So it was a very good solution. And here is the distribution of cloud top from the radar and from the simulation of the model. So it's the number of events with cloud top at 3, 6, 9, 12, 15 kilometers. So you can see that the model have a good behaviors showing that maximum after around 7, 8 kilometers. But model produce much more cloud tops with small cloud tops and also high. And when you introduce the three-dimensional solution, you decrease this mistake in this place by the simulation. And here is the skill of the model using the symmetric stream dependence score for 3D. Here we also simulate different mixing layer inside the clouds in the turbulence. So you have 1, 3, and there is not too much effect change the layer of the mixed layer cloud inside the turbulence, but the score, the skill of the model increase with the time with the use of 3 dimension. And here is the effect in the size of the cells using you can see that 1D, a lot of small guys, and 3 dimension, you reduce the distribution of size nearly to the same as observed for these 2 days you have studied, because you have radar data during these 2 days, a full day of radar data. And this was for brightness temperature, means clouds, and this was using radar, means rainfall. So we also see that it's reduced more than was expected to have in the real life. And the lifetime duration was for the rain cells, rainfall cells from the radar. And this is the observation from the radar. This is from 1D, and it's for the 3D dimension that reduced that's put together, but reduced too much the life cycle duration of the small life cycle duration. So we're trying to understand what you can do better to improve the quality of the model, and then we separate a histogram of brightness temperature for the small cells and for the big cells. So for the small cells, we can see that the model really have much more colder temperature cloud tops than it's observed, and the 3D reduced, but reduced. So the problem with the model that produce too much small cells and very deep. And for the big guys, this is the histogram, so the satellites show that are colder. And so for the big guys, the mud does not show as deeper as we expect. And the 3D reduce more than was observed. So we still are working on, and you see that the solution is to have an entrainment that depends from the size of the cells. It's not only because 3D also does not act exactly as we expect to have. So the conclusion we have is that model produce more small cells and short life cycles and very deep than the one observed by satellite and radar. 3D turbulence improves description of cloud organization in space and time. Does not change the general histogram of cold clouds. So there is a kind of cloud that's not solved by this problem. So what is we are going to work now? It's a scheme taking account the size, the life cycle distribution, to turning the parameterization of turbulence or the entrainment. And this is one important point that's for the people which working with the intercomparison. All these radar at the same resolution or satellite images are data of, already available in my computer, but I increase the size and duration of the big guys. So we are working on the sensibility before to make this parameterization. We are working the sensibility of this, trying to running with 0.5 and 1.5 to see the effect before to use this result. So thank you. Or? No, what I show is the 20 dBz cells, larger than 20 dBz. So I filter out because these radars are the radars S-band that was not worked by the Shruva, was the Air Force gave to us, so it's not science radar. So you have a lot of noise down to 20 dBz. So I just show larger than 20 dBz. No, no, it didn't touch. It just have the hypothesis that was entrainment and trying to work with turbulence and entrainment. But that's good to try to see. Yeah, there is a new paper that's going to be published in Monthly Weather Review in 2 or 3 months that I get access that also show this. And I review another paper for Journal Atmospheric Science, and then they show also that has much more small cells. So it's I think it's and also the simulation with Yola, it's very clear when Renato show that there is too much small guys and very deep than this observed. Yeah, it's the Kessler parameterization with adjustment from Pinty and others collaborators. So it's a traditional bulk parameterization. No. There is Graupo, is no 6 species. No, it's not explicitly described. It's the bulk parameterization.
Entrainment. When in the past we ran 1D models, the entrainment was inversely proportional to the radius of the cloud. So it's basically in the same. His very first papers on
Jonas Simpson.
yeah. They already had this feature. The entrainment would be inversely proportional to the radius.
And this is something that is observed, so it needs to be solved. I don't know if the solution will be this. We are going to try to find, but.
And just another question. Did you try running with 1 kilometer resolution?
No, it's just 2 kilometers.
Because Saulo Freitas did some runs comparing the 1 kilometer and the 2 kilometer for the Petropolis case, the one that rained so much. And 1 kilometer was much better in cloud organization because for BRAMs, you have a better representation of cloud microphysics at 1 kilometer than at 2.
Yeah, I agree that it's better high resolution. You're also trying to convince the guys to have less simulation with 100 meters to see the effect. But I think you need better results to get that.
Do we have any other comment? We are now having a coffee break. We will be back here at 11 sharp.